Yeah, good evening, ma'am. Just give me a moment. Yesterday, we were learning about the concept called as catalysis in the next part of the chapter surface chemistry, the second part. In the previous classes, we learned about adsorption, different types of adsorption, isotherm, all that. Now, just to have a continuity, we learned yesterday, in the previous class, we learned the term catalysis, types of catalysis, and characteristic of the catalysis also. Just to have a continuity, again, we'll brush through the characteristics of a catalyst, and then we'll continue with the theories of catalysis and some questions based on catalysis and go to the third part of the chapter today. The following are the characteristics which are common to most of the catalyst. The first point is catalyst remains unchanged in mass and chemical composition at the end of the reaction. Now, for example, if I take KClO3, it is potassium chlorate. This potassium chlorate, when we heat in the presence of manganese dioxide, it will decompose to form potassium chloride, giving you oxygen. Now, in order to bring about this reaction, the catalyst is manganese dioxide. So, manganese dioxide is taken in very less quantity, around 0.4 grams of manganese dioxide. So during the process, manganese dioxide will take part in the reaction. At the end of the reaction, the catalyst will be regenerated, and the amount of manganese dioxide at the end of the reaction will be again 0.4, and the composition will be MnO2 itself. So that is what the first point says. Catalyst remains unchanged in mass and chemical composition at the end of the reaction. The second point is small quantity of catalyst is generally sufficient to catalyze almost unlimited reactions. So here, maybe you take 2 grams of potassium chlorate and the catalyst is 0.4. That is 5:1 ratio. Catalyst is very small compared to the reactant. So very small quantity of catalyst is enough to bring about the sufficient catalytic reactions. The third, small, for these examples are okay. The third point is, The third point is, catalyst cannot initiate the reaction, meaning the catalyst will not be in a position to start the reaction. Catalyst will only alter the rate of a reaction, only increase the speed or decrease the speed of a reaction. So a catalyst cannot start the reaction. Therefore, the statement says the catalyst cannot initiate the reaction. The fourth point is the catalyst is generally specific in nature. Catalysts are highly specific in nature. What do you mean by catalysts are highly specific in nature? Now, for an example, for the synthesis of ammonia by Haber's process, the catalyst is finely powdered iron. We cannot use any other metal or any other catalyst. So only iron can bring about this reaction more effectively, more efficiently. Now, for contact process, for the manufacturing of sulfur dioxide, so oxidation of sulfur dioxide is done using vanadium pentoxide or using platinum. So no other iron cannot bring about this reaction, nor vanadium pentoxide can bring about this reaction. That is why we say catalysts are generally specific in nature. They are highly specific in nature, more specific, to be more clear. The fifth point is catalysts do not change the positions of the equilibrium. So the catalyst will not change the position of the equilibrium. The catalyst catalyzes both forward and backward reaction to the same extent with a reversible reaction. Thus, there won't be any change in the equilibrium. So the equilibrium constant will remain same, whether we are using catalyst or we are not using catalyst. The equilibrium constant will remain same. That is what it means. the catalyst will not change the position of the equilibrium. It will remain same. And we learned few more terms also, catalytic promoter and catalytic poison. Now, in case of synthesis of ammonia by Haber's process, iron is a catalyst. We use a metal molybdenum, MO. This molybdenum will increase the efficiency of iron. Since molybdenum increases the efficiency of iron, we say molybdenum is a catalytic promoter because it increases the activity of the catalyst. It increases the efficiency of the catalyst. So any chemical substance which increases the activity of a catalyst will be called as catalytic promoter. Example, molybdenum. So here they've given molybdenum. Now, in case of catalytic poison, substance which destroys the activity or decreases the activity of the catalyst is known as catalytic poison. Now, for an example, traces of arsenic oxide will deactivate or will reduce the activity of platinized asbestos or will reduce the activity of platinum. All right. Therefore, arsenic oxide will be called as a catalytic poison. And the eighth character of a catalyst is change of temperature, alter the rate of catalytic reaction as it does from the same reaction in the absence of catalyst. So change of temperature alters the rate of catalytic reaction as it does in the same reaction, the absence. So absence of catalyst also is influenced by temperature. Likewise, presence of catalyst is also influenced by temperature. So temperature at which the catalyst has a maximum activity is called as optimum temperature. So temperature at which the catalyst shows maximum activity will be called as optimum temperature. Now, for an example, in case of Haber's process, the temperature is around 500 Kelvin. 500 degrees Celsius. So at around 500 degrees Celsius, 450 to 500 degrees Celsius, iron will be more active. So therefore, the optimum temperature of iron is around 450 to 500 degrees. So this also we have learned. The positive catalyst lowers the activation energy. Effect of catalyst, we learned the same concept. We learned how catalyst will increase the speed of the reaction. Catalyst will increase the speed of reaction by decreasing the activation energy. So this is potential energy versus reaction coordinate or reaction path. Now, what happens in the absence? This is A and B reactants. In the absence of catalyst, the energy required for the reaction to take place is very high. This is the energy of activation required. Only when this barrier is crossed, we get the product. But for the same reaction, when you use a catalyst, the reaction takes place in a different path and at lower activation energy itself, it forms a complex and that will decompose to give you product. So in the presence of catalyst, the reaction will take a different path by reducing the energy of activation. Therefore, the reaction will be faster. This is what we have learned in the previous class. Now, we're going to learn theories of catalysis. There are two theories of catalysis. One is called as intermediate compound formation theory. The other one we have is called as adsorption theory. Intermediate compound formation theory. The second one is called as adsorption theory. Now, this intermediate compound formation theory will be generally applicable for homogeneous catalysis. Homogeneous catalysis. So what is homogeneous catalysis? A catalytic reaction in which the physical states of the reactants and the catalyst are same is called as homogeneous catalysis. So homogeneous catalysis always follow intermediate compound formation theory. This theory was proposed by Clement and Desormes in 1806. According to this theory, the desired reaction is brought about by a path involving the formation of unstable intermediate compound, followed by its decomposition to a desired product. with the regeneration of the catalyst. So I told you intermediate compound theory is applicable for homogeneous catalysis. Now, intermediate compound formation theory, intermediate compound may be formed in either of two ways. Intermediate compound is reactive and reacts with the other reactant. Now, AB plus X. AB is a reactant. X is also a reactant. So B reacts with X, forming an intermediate compound plus A. This BX will react with the catalyst to form CB plus X. This is first. The second one is, this is more appropriate. The second one, what we're going to talk about, is more appropriate. Now, A plus B giving you the product. This product, we can name it as P. Instead of writing the whole word, product, we will just name it as P. This is the reaction in the absence of catalyst. It is a slow process. Now, the same reaction, when you perform in the presence of a catalyst, you get a product, and this is fast. So what happens is the reactants A and B reacts with the C to form an intermediate compound. This intermediate compound will have extremely high energy. Since this intermediate compound is extremely high energy, it will decompose to give you product and give back the catalyst. This is the general mechanism for the intermediate compound formation theory. Generally, intermediate compound formation theory is applicable for homogeneous catalysis. So A and B are reactants, P is product. This reaction is extremely slow. Now A and B are reactants. In the presence of catalyst, you get a product, and the product formed in the presence of catalyst is extremely fast. So why the reaction is fast in the presence of catalyst? Because the reactants A and B will react with the catalyst to form ABC, an intermediate compound, which has extremely high energy. It is highly unstable. So this will decompose to give products and give back the catalyst. The next thing what we have is called as adsorption theory. This adsorption theory is generally applicable for heterogeneous catalysis. So heterogeneous catalysis, catalytic reactions otherwise, follow adsorption theory. Now, in case of adsorption theory, so we can write A plus B giving you a product. It is slow. So in the presence of a catalyst, you get a product, and this is called as fast. So what happens is, now for an example, if you take nitrogen and hydrogen in the presence of iron as a catalyst, you get ammonia. You get ammonia. So what happens if you take this as iron, which is a catalyst? Now this nitrogen and hydrogen gets adsorbed on the catalyst. Nitrogen and hydrogen gets adsorbed on the catalyst. When they get adsorbed on the catalyst, they react with each other on the surface of a catalyst to form ammonia. So product is formed on the surface of what? The catalyst, ammonia. Once the product ammonia is formed, this will undergo desorption to give you back ammonia. So therefore, this is called as adsorption theory, because the reactants and products are formed on the surface of the catalyst. Once the product is formed, the product gets desorbed, leaving what? The catalyst. Therefore, this theory is applicable only for heterogeneous catalysis. Heterogeneous catalysis. Now, two types of theory we learned. One is intermediate compound formation theory. The other one is adsorption theory. Now, this is also important. Even though it is a biochemistry part, we are going to learn this in our syllabus. It's there, enzyme catalysis. Enzymes are called as biocatalyst. Enzymes are called as biocatalyst. So enzymes will catalyze biochemical reactions. Biochemical reactions. So all the reactions taking place in our body will be catalyzed by enzymes. Therefore, enzymes are called as biocatalysts. Now, mostly or generally, enzymes are proteins. Enzymes are proteins. Enzymes are complex nitrogenous substances. These are actually protein molecules of higher molecular mass. So enzymes are complexes or complex nitrogenous substances. These are actually protein molecules with high molecular mass. Enzyme catalyzes numerous reactions, especially those connected with natural process. So enzymes catalyzes numerous reactions, especially those connected with natural process, whatever is happening in our body. Now, numerous reactions occur in the body of animals and plants to maintain the life process. These reactions are catalyzed by enzymes, and the enzymes are thus termed as biochemical catalysts or biocatalysts. And the phenomenon is known as biochemical catalysis. Nitrogenase, an enzyme present in bacteria on the root nodules of leguminous plants, such as peas and beans, catalyze the conversion of atmospheric nitrogen to ammonia. So nitrogenase is an enzyme which catalyzes the conversion of atmospheric nitrogen to ammonia. In the body, human body, the enzyme carbonic anhydrase catalyzes the reaction of carbon dioxide to water. And in the manufacturing of ethanol, ethyl alcohol, also we have the catalysts. And the last part of the catalyst is zeolites. What are zeolites? Z-E-O-L-I-T-S. Zeolites are sodium aluminum silicates. Sodium aluminum silicates. Sodium aluminum silicates. Zeolites are aluminosilicates or sodium aluminum silicates of the general formula mx by n AlO2 x times O3 x times SiO2 y times dot MH2. So this is the general H2O, the general representation of the zeolite. Mx by n Al2O3 x times AlO3 x times plus AlO2 x times SiO2 y times MXH2O molecule, where M may be a simple cation like sodium, potassium, or calcium. N is the charge on the simple cation. M is the number of molecules of water. M is the number of molecules of water. Some well-known zeolites are erionite, E-R-I-O-N-I-T-E, Na2K2CaMg, Al O2 twice, SiO2 twice, 6H2. Gemelinite, G-E-M-A-L-I-N-I-T, Na2Ca, AlO2 twice, SiO2 twice, 4 times, 6H2. This is important. ZSM5. Oh, sorry. ZSM5. This you can remember. 1 or 2 examples, if you remember, that should be fine, because they'll ask you what is zeolites, give an example or something. It's a very vast topic. We are just introducing what is zeolite. That's all. ZSM. X times AlO2 x times SiO2 96 minus x dot 16H2. This is the general representation of a zeolite. And Linde A, synthetic zeolite. The characteristic features of zeolite is openness of the structure, which permits cavities of different sizes. So what is the feature of zeolite? It is openness of the structure, which permits cavities of different sizes. The open structure is provided by silica, in which aluminum occupies x by x plus y fraction. All this is highly theoretical, not necessary for us to understand in detail at this stage. So ZSM5 Al2OX, SiO2 96-X, and 16H2. This is a representation of zeolite ZSM5. This ZSM5 converts alcohol to gasoline, alcohols to petrol by dehydrating alcohol and producing a mixture of variety of hydrocarbons. So ZSM5 is used to convert alcohols to gasoline, convert alcohols to petrol by dehydrating the alcohol and producing many number of or wide variety of hydrocarbons. Now, some of the questions based on catalysis quickly, and then we will learn with the topic colloids. The first question: catalyst remains unchanged at the end of the reaction as regards quality, chemical composition, quality and chemical composition, and physical state. So catalyst remains unchanged at the end of the reaction as regards with chemical composition, only with respect to chemical composition. Quality may vary. Initially, you may take crystals. Finally, after the reaction, it may be in a fine powdered state. So physical state will vary. Quality may vary, but the chemical composition remains same. And hence the answer for this question is option B. The next one, negative catalyst. See, in modern days, negative catalyst is called as inhibitors, which chemical substances which slows down the reaction. Chemical substances which slows down the reaction is called as inhibitors. In the earlier days, we were calling it as a negative catalyst. So negative catalyst retards the rate of a reaction, promotes side reaction, promote backward reaction, all of these. So retard means slow down rate of the reaction. Hence the option is A. The next question: which of the following acts as a negative catalyst? Which of the following acts as a negative? Glycerol in the decomposition of hydrogen peroxide, lead tetraethyl as an anti-knock, ethanol in the oxidation of chloroform, all of these. So glycerol, lead tetraethyl, or tetraethyl lead, or ethanol in the oxidation of chloroform. All these three are the examples for negative catalyst. Hence, the answer is option D, all of these. Next question. Potassium metasulfite used as food preservative is a homogeneous catalysis, heterogeneous catalysis, it is a positive catalyst, or it is a negative catalyst. Normally, food preservatives are used to slow down the decomposition. So since it slows down the decomposition of the food, it will be an example for negative catalyst. Potassium metabisulfite is a food preservative which is used to slow down the decomposition of the food. Hence, it's an example for negative catalyst. Now, KClO3 decomposes to form KCl and O2. A small amount of manganese dioxide added makes the reaction go faster. This is because manganese provides better manganese dioxide provides better contact. Manganese dioxide acts as a catalyst. Manganese dioxide provides energy to potassium chlorate. None of these. So manganese dioxide increases the speed of the reaction because it acts as a positive catalyst. It acts as a catalyst. Therefore, the answer is option B. Which of the following is used to retard the oxidation of chloroform? We learned it in the previous question. So ethanol is an example, or ethanol is an inhibitor which retards the oxidation of chloroform, which slows down the oxidation of chloroform. Next question. The process catalyzed by one of the products of the reaction is called as anti-catalysis, negative catalysis, autocatalysis, acid-base catalysis. So during the titration of oxalic H2C2O4 oxalic acid versus KMnO4, during the titration in acid medium, you get Mn2 plus as the ion. This Mn2 plus, which is one of the product, manganese sulfate or manganese chromate, which is a product, in that manganese sulfate, this manganese ion will catalyze this reaction. So therefore, these kind of reactions are called as autocatalysis. Autocatalysis is a catalytic reaction in which one of the product formed itself will behave like a catalyst. Therefore, the answer is option C. In the titration between oxalic acid and acidified potassium permanganate, manganese salt formed catalyzes the reaction. The manganese salt is a promoter, a positive catalyst, and an autocatalyst. Just we learned in the previous question, it is an autocatalyst. The next question. The reaction used in contact process for the manufacturing of sulfuric acid, SO2 plus O2 giving you SO3. This is sulfur trioxide. This is oxidation of sulfur dioxide to sulfur trioxide. The role of catalyst in this process. Here the catalyst is vanadium pentoxide, or they can use platinum, rhodium catalyst, platinum, asbestos. Speed up the forward reaction so as to yield more sulfur dioxide, slows down the backward reaction leading to the same result, reach the state of equilibrium quickly, make the reaction more exothermic so the process can be carried out at low temperature. So the purpose of using catalyst for a reversible reaction is to make the reaction reach the equilibrium state quickly. Hence, the answer is option C. Next, the enzyme activity is maximum at 300 Kelvin, 310 Kelvin, 320 Kelvin, 330. And the enzyme activity, the activity of enzyme is maximum at 37 degrees Celsius. That is 273 plus 37. It will be 310 Kelvin. So this will be called as optimum temperature. So enzyme activity is maximum at 37 degrees Celsius. Therefore, the optimum temperature for enzyme is 37 degrees Celsius. Hence, the answer for this question is option B. The 11th question. The enzyme which catalyzes the conversion of glucose to alcohol. The enzyme which catalyzes the conversion of glucose to alcohol is invertase, carbopeptidase, zymase, and maltase. The enzyme which catalyzes the conversion of glucose, sucrose, will be converted to glucose and fructose by an enzyme called as invertase. And this glucose will be converted to ethanol, C2H5OH, by an enzyme called as zymase, ZYMASE. So the answer for this question is option C, zymase. Oh, the next question. The efficiency of a solid catalyst depends on its particle size, molecular weight, solubility, and color. Efficiency of a solid catalyst depends on particle size, because as the particle size decreases, surface area will increase. So the efficiency of the catalyst, solid catalyst, depends on a particle size. Catalytic activity is maximum at peaks, cracks, edges, smooth surfaces. Minimum, not maximum. The catalytic activity is minimum at smooth surfaces. They are maximum at peaks, cracks, and edges. The next one, the theory of heterogeneous catalysis is based upon the phenomenon. Heterogeneous catalysis, the theory is based upon the phenomenon adsorption, absorption, dissociation, decomposition. We clearly discussed heterogeneous catalysis will undergo adsorption theory. It will follow adsorption theory. So the answer for this question is option A. The next one is, in the manufacturing of nitric acid by Oswald's process, the catalyst used is finely divided iron, platinum, rhodium, gauze, vanadium pentoxide, molybdenum. So the manufacturing of nitric acid by Oswald's process, the catalyst used is platinum, rhodium, gauze. Platinum and rhodium gauze. The next question. Shape's selective catalyst is the reaction catalyzed by zeolites, enzymes, platinum, Ziegler-Natta catalyst. Shape selective catalysis is a reaction catalyzed by zeolites. Option A. Next question. The activity of an enzyme becomes ineffective at low temperature, at atmospheric pressure, at high temperature, in aqueous medium. So the activity of enzyme becomes ineffective at a high temperature. Greater than 37 degrees Celsius, the activity of enzymes keeps on decreasing. The next question. Which of the following is not correct for enzyme catalysis? The enzyme activity is maximum at optimum pH, which is between 5 and 7. Each enzyme is specific for a given reaction. The favorable temperature range for enzyme activity is 50 to 60 degrees Celsius. It is wrong. It is maximum activity is around 37 degrees Celsius. The enzyme activity increase in the presence of certain substance called as coenzyme. This is also true. All these are true, and this is the wrong, not favorable condition. Therefore, the answer for this question is option C. 19th question. Which one of the following statements is incorrect about enzyme catalysis? Enzymes are mostly proteinous in nature. True. Enzymes are highly specific. Very good. True. Sorry, not good. Very true. Enzymes are denatured by UV rays and at high temperature. This is also true. Enzymes are least reactive at optimum temperature. This is wrong. Enzymes are highly reactive at optimum temperature. Hence, the wrong option or the incorrect statement about enzyme is option D. Which of the following statements is correct about solid catalyst? Which of the following statements is correct about solid catalyst? Catalyst is required in equal amount as reactant present. Wrong statement. Catalysts are required in small amount. Catalyst activity of a solid catalyst does not depend upon the extent of chemisorption. Chemical adsorption, no chemical adsorption here. All right, it's only physical adsorption on a solid catalyst. Next, desorption is not important for a solid catalyst to act as a good catalyst. No, desorption should happen. Product is formed on the surface of the catalyst. If the product does not undergo desorption, then there is no point in using the catalyst. Same reactants may give different products by using different catalysts. This is a wrong statement. So catalyst will not give different products by using different catalysts. Catalyst will not decide the product formed. Therefore, the wrong statement here is option D. So these are the topics which we are supposed to learn with respect to catalysis. The next concept what we are going to learn is colloidal state. Colloidal state. Now, what is this colloidal state? What are colloids? Now, this term colloids, first Michael Faraday prepared the first colloidal system. It was termed not by him, but now in modern days, these colloidal systems are called as nanoparticles. These colloidal systems are called as nanoparticles now in modern terminologies. Now, what is this colloidal state? The foundation of colloidal chemistry was laid by an English scientist, Thomas Graham, in 1861. The credit for various advances in this field goes to eminent scientists like Tyndall, Hardy, Zsigmondy, Dhar, Indian Bhatnagar, and others. So, the foundation of the colloidal chemistry was laid by an English scientist, Thomas Graham, in 1861. The credit of various advances in this field goes to eminent scientists like Tyndall, Hardy's, Zsigmondy, Dhar, Bhatnagar, and others. Now, Thomas Graham classified the soluble substances into two categories. Thomas Graham classified the soluble substances into two categories, depending upon the rate of diffusion, through animal and vegetable membranes or parchment paper. So Thomas Graham classified soluble substances into two categories, depending upon the rate of diffusion through animal and vegetable membrane or parchment paper bag. And the first one, he named it as crystalloids. They have higher rate of diffusion and diffuse from parchment paper bag. All organic acids, bases, salts, and organic compounds such as sugar, urea, all these are called as crystalloids. We're going to learn about these crystalloids in detail further. Now, crystalloids, they have higher rate of diffusion. Please remember this for now. Now, colloids, in Greek, kolla means glue-like. The meaning is glue-like, sticky. They have slower rate of diffusion and cannot be diffused from parchment paper bag. Parchment paper bag. Parchment paper bag is a semi-permeable membrane. It's made of cellulose. Parchment paper bag. Starch, gelatin, gums, silicic acid, hemoglobin, all these are the examples for colloids. The above classification was discarded. That is, the term colloid does not apply to a particular class of substance, but a state of matter like solid, liquid, and gas. Any substance can be brought into colloidal state. So this classification was discarded because the term colloid does not apply to a particular class of substance, but it's a state of matter like solid, liquid, and gas. Any substance can be brought into colloidal state. The colloidal state depends on particle size. If is regarded as intermediate state between true solution and suspension. Now, features of three types of solutions. We have to learn the features of three types of solution. The first one is a suspension. The second one is colloidal solution. Third one is true solution. This true solution was also called as crystalloids. True solution are also called as crystalloids. Now, what's the nature? Any suspension is heterogeneous. Just visualize, if we take a little of sand and put in water, these sand particles will dissolve sand particle will settle at the bottom. It will get suspended at the bottom. It will not have any kind of interaction with the water. It will just settle at the bottom. So therefore, we can see the sand particles and also water molecule. We can differentiate. So those are called as heterogeneous system. Now, colloidal solution, it is also a heterogeneous system. Now, we have gold sol, example, gold particle dissolved in water, silver sol. We will learn about all this in detail, silver sol. So gold particles distributed in water, silver particle distributed in water will be called as an example for a colloidal solution. This colloidal solution is also heterogeneous. Colloidal solution is also heterogeneous. Next, what we have is a true solution. True solution is homogeneous. Homogeneous. Now, for an example, sugar solution. Sugar, when you dissolve it in water. Sugar and water. Sugar will dissolve in water. Is it possible for us to differentiate sugar molecules and water? It's not possible. It just looks like water. Therefore, those kind of solutions are called as homogeneous solution, or it's also called as true solutions. Now, the particle size, if the particle size is greater than 100 nanometers, nato stands for 1 nanometer stands for 10 to the power, minus 10 to the power minus 9 meters. A very small particle. If the particle size is greater than 100 nanometers, then the solution will always form suspension. So when the particle size is greater than 100 nanometer, it is possible for us to see it through our eyes. So colloidal solution. This colloidal solution is also a heterogeneous solution in which the particle size ranges from 1 nanometer to 100 nanometers. Whenever the particle size ranges from 1 nanometer to 100 nanometer, if the particle size ranges between 1 nanometer to 100 nanometer, then the solution which is formed is called as a colloidal solution. And for true solution, the particle size will be lesser than 1 nanometer. So when the particle size is lesser than 1 nanometer, it will form a true solution. It will completely dissolve in water or any of the solvent. It forms a homogeneous mixture because the particle size is less than 1 nanometer. Next, separation by ordinary filtration. Ordinary filtration, ultrafiltration. Suspension can be separated by ordinary filtration as well as ultrafiltration. Colloidal solution. So ordinary filtration is not possible, and ultrafiltration is possible. Now, in case of a true solution, ordinary filtration is not possible, nor ultrafiltration is possible. We cannot separate the solute and solvent of a true solution by either ordinary filtration or ultrafiltration. Settling of the particles. Suspension settle under gravity. Now, colloidal solution will not settle under gravity. It will settle only on centrifugation. True solution will not settle. If you take sugar and dissolve it in water, sugar particle will dissolve in water and it forms a true solution. After some time also, the sugar particle will not settle at the bottom. It will not settle. Appearance. Suspension appears, 1 minute. Suspension, appearance of suspension is opaque. Appearance of suspension is opaque. Colloidal solution is transparent and generally transparent, and for a true solution, it is transparent. We are going to learn the Tyndall effect, Brownian movement in later classes. Now, suspension shows Tyndall effect. Colloidal solution shows Tyndall effect. Remember, the true solution does not show Tyndall effect. Diffusion of particles. So suspension does not diffuse. Colloidal solution diffuses slowly through a semi-permeable membrane. True solution diffuses rapidly. Brownian movement. Suspension may show Brownian movement. Colloidal solution shows Brownian movement. And in case of true solution, the Brownian movement is negligible. So this is the difference between a true solution, suspension, and a colloid. Basically, you should remember colloid is a heterogeneous system in which the particle size ranges from 0 to 100 nanometer. Very important point. Very important point. 0 to 100 nanometer. Now, coming to the phases of colloids and their classification. Phases of colloids. We know that a colloid solution is of a heterogeneous nature. It consists of two phases, which are as follows. One is internal phase. It is called as dispersed phase. This dispersed phase is also called as discontinuous phase. The second one is called as external phase, or it's called as dispersion medium. It's a continuous phase. Now, dispersed phase, it is the component present in small proportion and is just like solute in the solution. For example, colloidal solution of silver in water Silver acts as a dispersed phase. Now, if you take, this is water, this is water, this is water completely. And if we take these all are silver particles, these are silver particles. And these particles is of size what? 1 to 100 nanometer. Therefore, this is called as a colloidal solution. So here, the silver particles are called as dispersed phase, and water will be called as dispersed medium. So silver particle, you can see it is not continuous. Here and there are silver particles, but water is continuous, complete. Therefore, water will be called as a dispersed phase, or it will be called as a continuous phase. So in simple words, we can say this dispersed phase, it is this component present in small proportion. This is just like solute in solution. And external phase, dispersion medium, it is a generally component present in excess. Compound present in excess. And just like solvent in the solution. So in case of colloidal solution of silver and water, water acts as a dispersion medium. Water acts as a dispersion medium. Classification of colloids, very, very important. This classification of colloids is colloids are classified into 8 types based on their dispersed phase and dispersed medium. So first one, dispersed phase is liquid, dispersed medium is gas. It's called as aerosol of the liquids. Example, fog, clouds, mist, etc. Dispersed phase is a solid. Dispersed medium is a gas. It's called as aerosol of solids. Smoke, volcanic dust, haze. Dispersed phase is gas. Dispersed medium is a liquid. It's called as foam. The colloidal system is called as foam. Soap, lather, lemonade froth, whipped cream, soda water. The next one is dispersed phase. This is very, very important. Dispersed phase is liquid. Dispersed medium is also liquid. It's called as emulsions. You can ask you, what is an emulsion? Emulsion is a colloidal system in which dispersed phase is a liquid and dispersed medium is a liquid. Example, milk, emulsified oils, medicines. This is also important. Dispersed phase is a solid. Dispersed medium is a liquid. It's called as salts, SYL. Most of the paints, starch and water, proteins, gold salt, arsenic sulfide salt, ink, all these are example for salts. So what are salts? Salts are a colloidal system in which the dispersed phase is solid and the dispersed medium is liquid. Next is dispersed phase is gas. Dispersed medium is solid. It's called a solid foam. Examples, pumice stone, styrene rubber, foam rubber. All these are examples for solid foam. Next colloid. Dispersed phase is liquid. Dispersed medium is solid. It's called as gels. What are gels? Colloidal system in which the dispersed phase is liquid and dispersed medium is solid. Example, cheese, butter, boot polish, jelly, curd, all these are gels. Next, dispersed phase is solid. Dispersed medium is also solid. It's called as solid sol. Example, ruby glass, some gemstones, etc. The next one, dispersed phase is gas. Dispersed medium is also a gas, and it is not a colloid. It does not form a colloid. Why? Because it forms a homogeneous mixture. Gas can mix with other gas in any proportion and forms a homogeneous mixture. We've been learning all the colloids are heterogeneous, but gas is a dispersed phase and gas is a dispersed medium. It does not form a colloidal system because it forms a homogeneous mixture. So this chart is important. Based on this chart, they can ask you a question. So kindly go through this chart, different types of colloidal system. The classification based on nature, interaction, all that we'll be learning possibly in the next class. Now, the types of colloidal system you can just go through.
Sir, are you there, sir? You are not audible, sir.
Yes, I'm there, ma'am. I want people
Okay,
to
sir.
look at this.
Okay, sir.
I thought I would, that's what ma'am, anyways, I'm done with ma'am. I'll stop the class now, ma'am. Thank you. Bye, ma'am.
Okay, sir. Thank you, sir. Thank you, sir.